At first light above the Himalaya, the world seems to empty itself of life. Rock turns to ice, wind tears at the ridgelines, and the air thins toward a point where human thought slows. Muscles fail, and every breath becomes an argument with physics. Yet across this high, cold barrier, wings continue to move. A skein of geese appears above a glacier, not drifting but climbing, each beat of the wing demanding oxygen from an atmosphere that offers almost none. Far away, over Africa, a vulture once rose so high it entered the flight path of a jetliner. Over the North Atlantic, swans have been recorded at heights where most creatures would be close to collapse. Today we're diving into why high-altitude birds choose to fly where oxygen fails. The question is not only how they survive there, it is why evolution keeps sending them upward at all, into air too thin for comfort, too cold for error, and too unforgiving for waste. In these journeys, altitude is not a spectacle. It is a biological decision, written into blood, lungs, muscle, and instinct. The emblem of this mystery is the bar-headed goose, a bird that breeds across Central Asia and the Tibetan Plateau, and winters in the lowlands of South Asia. To move between those worlds, many of these geese face the highest mountains on Earth. For decades, mountaineers reported seeing them astonishingly high above the Himalaya, even above 8,000 meters. Modern tracking has sharpened the picture. Most bar-headed geese do not cruise casually over the highest summits. They usually cross at lower elevations, often between about 5,000 and 6,000 meters. And they tend to thread through valleys and lower passes, flying surprisingly close to the terrain beneath them. In one large tracking study, 95% of flight locations were below roughly 5,784 meters, and the birds often stayed only a few hundred meters above the ground. This matters because it reveals that these birds are not chasing altitude for its own sake. They are minimizing it wherever they can. And still, even their low route would be a physiological emergency for most vertebrates. They can climb 4,000 to 6,000 meters in 7 to 8 hours, sometimes crossing the mountain barrier in a single day. The reason they accept this cost is simple, and severe geography leaves them little choice. Going around the Himalaya would add major distance, time, and energetic expense. Flying over, even at the lowest feasible line, is the shortest path between breeding and wintering worlds. Thin air is not the goal. It is the price of a direct route. That begins to answer the why, but not the deeper puzzle. Flight is already one of the most oxygen-demanding things an animal can do. At sea level, a bird in active flight can increase oxygen consumption 10 to 15-fold over resting levels. At altitude, the challenge doubles back on itself. Oxygen partial pressure falls, so each breath yields less. Air density also falls, so each wing beat generates less lift. A bird in thin air must work harder with less fuel available. The solution begins with a respiratory system unlike our own. Bird lungs do not inflate and deflate in the same tidal way mammalian lungs do. Instead, air sacs act as bellows, moving air in a largely unidirectional stream through rigid lungs. Inside, blood and air meet in a cross-current exchange system that is exceptionally efficient at extracting oxygen under hypoxic conditions. Birds also tolerate the chemistry of overbreathing better than mammals. They can keep ventilating hard even as carbon dioxide drops and blood chemistry shifts. Their lungs present a large exchange surface with a very thin diffusion barrier. Their hearts are relatively large. Their flight muscles are densely supplied with capillaries. In other words, the avian body is already biased toward moving oxygen rapidly from atmosphere to tissue. High-altitude birds do not invent an entirely new machine. They begin with one of evolution's most efficient aerobic designs, then push it further. In the bar-headed goose, those refinements become astonishingly specific. Its hemoglobin binds oxygen more effectively than that of related lowland birds, an advantage linked largely to a single amino acid substitution that changes how readily oxygen is loaded in the lungs. Its lungs are proportionally larger than those of many other waterfowl. When oxygen becomes scarce, it can hyperventilate intensely, up to 7 times the normoxic resting rate in experimental conditions. And deep inside its flight muscles, the architecture of survival becomes microscopic. Compared with lower altitude geese, bar-headed geese have more oxidative muscle fibers, more capillaries per fiber, more even capillary spacing, and a redistribution of mitochondria toward the cell membrane, closer to the blood supply. That shift shortens the distance oxygen must diffuse before it reaches the engines of aerobic metabolism. It is an elegant kind of spatial economy. Do not ask oxygen to travel farther than necessary. These adaptations are not dramatic in the way antlers or teeth are dramatic. They are subtler and more powerful than that. They turn a dangerous climb into a repeatable migration. They let the bird keep its tissues supplied even when the sky is offering little more than a trace of what sea level would provide. The goose is not merely enduring altitude. It is anatomically budgeted for it. But anatomy alone does not explain performance. In recent wind tunnel studies, bar-headed geese trained to fly in simulated high-altitude conditions revealed something even more intriguing. As oxygen levels dropped to those equivalent to extreme elevations, their heart rates did not rise beyond those seen in normoxic flight, and wingbeat frequency remained largely unchanged. Instead, the birds appeared to lower overall metabolic rate by around 16 to 20% in hypoxic flight. They also cooled venous blood during flight, a shift that likely helps hemoglobin load oxygen more effectively. This suggests that the bar-headed goose does not solve the high-altitude problem simply by driving harder. It solves it partly by becoming more economical. Less waste, less excess heat, less oxygen diverted to non-essential processes. Even the timing of migration seems shaped by these constraints. Observations and field studies indicate that bar-headed geese often migrate at night or in the early morning, rather than waiting for stronger daytime updrafts. The logic may be aerodynamic as much as meteorological. Colder air is denser, calmer conditions reduce turbulence, and flying close to terrain can help the birds avoid the steepest energetic penalties of climbing into even thinner air. They are not romantic conquerors of the sky. They are disciplined accountants of cost. Every meter gained must justify itself. Every route is negotiated against pressure, temperature, wind, and terrain. What looks from below like a heroic crossing is, from the bird's point of view, a strict physiological compromise. And the bar-headed goose is only one version of the answer. In the Andes, birds such as the Andean goose and the crested duck live year-round between roughly 3,000 and 5,500 meters. They do not merely pass through hypoxia, they build their lives inside it. Studies comparing these resident Andean birds with migratory bar-headed geese show that evolution can solve the same oxygen problem in very different ways. When exposed to hypoxia, bar-headed geese respond with a robust increase in ventilation and heart rate, mobilizing oxygen transport rapidly for a temporary extreme effort. The Andean species are different. They increase lung oxygen extraction and boost stroke volume rather than relying so heavily on frantic breathing or faster pulse. The contrast is revealing. Migration favors a system that can be switched on for extraordinary performance. Residency favors structural efficiency, lungs and hearts tuned for constant work in chronic thin air. Both strategies succeed, but for different ecological reasons. A migrant needs to survive a crossing. A resident needs to spend a lifetime there, feeding, breeding, escaping predators, raising young. Even at the molecular level, high-altitude birds from different lineages repeatedly evolve hemoglobins with elevated oxygen affinity, but not always through the same genetic changes. Evolution does not produce a single ideal blueprint for living above the clouds. It produces a family of solutions, each tailored to the kind of altitude life demands. Then there are the birds for whom altitude is not a corridor between seasonal homes, but a hunting ground, a search pattern, or an atmospheric tool. In 1973, a Rüppell's griffon vulture collided with an aircraft over Côte d'Ivoire at 11,300 meters, still the highest confirmed altitude recorded for a bird. That does not mean the species lives routinely at jetliner height. It is rarely seen above 6,000 meters. But the record is a reminder that soaring birds can enter extreme layers of the atmosphere when thermals and large-scale air movements carry them upward. For vultures, height expands vision and search range. A scavenger looking for carcasses across immense African landscapes benefits from covering ground at minimal muscular cost, circling in rising air, rather than paying for every meter with active flapping. The same principle echoes in other species. On 9 December 1967, about 30 whooper swans were confirmed on radar at just over 8,230 meters, while traveling from Iceland toward wintering grounds around Loch Foyle. Such moments are rare, but they reveal something crucial. Birds do not encounter altitude, only because mountains stand in the way. Sometimes the sky itself becomes a route with strategic properties: winds, temperatures, visibility, or terrain avoidance that make a difficult height worth entering. In that sense, choice is evolutionary rather than conscious. Birds rise because food, migration timing, breeding access, or energy savings reward individuals that can use a hostile layer of atmosphere others cannot. Altitude becomes ecological space. Thin air, once a limit, becomes a niche. What makes these stories so compelling is that they are not just about endurance. They are about the repeated conversion of impossibility into routine. A mountain barrier becomes a migratory shortcut. Chronic hypoxia becomes a habitat. Rising columns of heated air become a way to search continents with almost no flapping at all. The common feature is not courage, but selective pressure. Birds do not fly high because height is noble. They fly high because, under certain conditions, natural selection has made altitude useful. The ones that could load oxygen faster, diffuse it farther, place mitochondria closer, enlarge a lung, alter a hemoglobin molecule, or time a flight into calmer, denser air were the ones that reached the breeding ground sooner, crossed the barrier more directly, found the carcass first, or survived long enough to reproduce. Over generations, the atmosphere itself becomes part of their anatomy. The sky shapes the blood, the root shapes the lung, and the limit that defeats one lineage becomes the opportunity that defines another. When we watch a line of geese crossing a ridge or a vulture circling into pale, cold light, we are watching evolution use the third dimension not as emptiness, but as a resource. And still, much of this high world remains beyond us. We know more now about flight altitudes, blood chemistry, muscle structure, and migration routes than any previous generation could have imagined. Yet the full decision-making of a bird in thin air is still partly hidden inside weather, terrain, experience, and instinct. We do not yet know all the cues that tell a goose when to climb, when to wait, when to pass through one valley rather than another, or how often extreme altitudes are chosen only because all safer options have disappeared. We know that birds have multiple solutions to oxygen scarcity, but we do not know how many remain undiscovered in remote mountain systems or among small species rarely tracked. Perhaps that is the deepest lesson in these flights. The upper atmosphere looks empty to us because we are poorly built for it. But to some birds, it is a place of passage, efficiency, even advantage, a landscape we only dimly understand because we enter it as trespassers. They move through it on inherited terms, and somewhere above the ridgelines, where pressure falls and sound seems to drain from the world, life is still rewriting the boundary of what a body can do.